With us today, we have George Bollendorf. George is the Marketing and Business Development Manager at Empower RF Systems. Also with us today is Paulo Correa. Paulo is the CTO at Empire RF Systems. And finally, we have Jon Jacocks. Jon is the President and CEO of Empower RF Systems.
Hello, everybody. I'm Jon Jacocks, President and CEO of Empower RF Systems. I would like to welcome you to today's session. We're going to make very good use of the next 30 to 40 minutes, walking through some illustrations and providing insights into how to choose and integrate high-power RF modules in your upcoming designs. I'd like to thank Global Spec for running the platform today, and certainly thanks to our partner in modules, Richardson RFPD. Let's go ahead and get started.
Thanks, Jon. This is George Bollendorf, the Marketing Manager at Empower RF, and I'm really excited about today's subject. There are some very interesting takeaways that you'll come away with, and one of my favorites, the truth about linearity. There are subtleties here that Paulo will cover, and I'm sure you'll learn something in that discussion. Paulo will also hit on the trade-offs between efficiency and linearity, and then also the differences between broadband and narrowband designs. You'll also learn about device technologies and a little more detail on GaN, where 50-volt devices come into play. And not to be underestimated, you'll get insight into the scope of work required when you decide to combine modules for higher power. For delivering on these key takeaways, we've arranged the presentation material as shown here, but before we get too far into it, you need to know what we mean by modules. We're talking solid state power amplifier modules, tens of watts to a couple hundred watts, 0 dBm in. And here on the right are illustrations of modules that we offer. And Jon is going to quickly cover our experience and expertise. Then Paulo will be hitting the more technical aspects of the topics.
Thanks, George. And let me quickly add some context. Empower RF Systems, LA-based with a design center as well in New York, we are in the business of high-power RF. You can see on the slide here the frequency coverage from HF up to X-band, the markets that are most applicable to the work that we do, and a very short description of basically the product portfolio, modules, air-cooled systems, and very high-power liquid-cooled transmitters. And building on that theme just a little bit, in why do we know modules? Obviously, we've been doing it for a very long time. The product configurations you see on the slide here, and really building on that illustration at the bottom of the slide, going from right to left, those are increasing levels of power, increasing levels of complexity. The output power ranges that we are routinely dealing with, as George mentioned earlier, tens of watts up to hundreds of watts in the module family, hundreds of watts up to hundreds of kilowatts in the high power combining end of our product line. We're excited to get started, and let's jump in on our first module slide.
To baseline the discussion, and not to be confused with an LNA or bidirectional module, what I'm showing here is a block diagram of a typical system which utilizes a PA module, which is shown in the red square. With the PA module, in order to get it to anything, you've got to have your RF or microwave source 0 dBm nominal. You've got to have a DC power supply. You probably have a coupler or some other way to meter the output power. And typically, because these are higher power, you're likely driving an antenna or other 50 ohm load. And important but not shown here, the module will typically have analog I/O for temperature sense, bias current monitoring, an alarm, and a PA enable, for example, that you'll need interfacing to. And digital I/O, including gain control, is available in some cases.
Okay, so let's take a quick look under the hood of a power module, and the illustration on top, the notional block diagram, as well as the actual photo that you see below, are representative of Empower RF Systems smart modules. You can see semiconductor devices, you can see multi-layer boards, you can see 3dB hybrids, but rather than me trying to elaborate on this, now's a great time to introduce our CTO and the architect of our next-gen systems, Paulo Correa. Paulo, can you talk a little bit more about this slide?
Okay, let's start by looking at this module as an independent module. Consider that the voltage that you need is always 28 volts or 48 volts or 50 volts that you apply to a standard module. And in this case, we have to internally generate all the rails required to generate the negative voltage for GAN and the plus and minus to bias the operational amplifiers. So all the ancillary power supplies are generated inside the module. You don't need to have any other sources of voltage than your primary voltage. Second thing is that this is based on microcontroller. So we have all the bias circuits are driven by the microcontroller. Therefore, there are no variable trim pots or variable resistor to adjust current on the devices. And in fact, if you look this picture and this block diagram, there is no variable components on our Empower modules. And furthermore, you have to consider that we have a smart unit and you have capability of connecting to it to use an RS-485 interface.
Thanks, Paulo, for that quick overview on that smart module. What we're looking at on the screen right now is a building block module, pretty basic, 28-volt DC version out of our COTS portfolio. For everybody in the audience, I'll give you just a second to kind of familiarize yourself with the different parameters. These are representative of the conditions that we test. And Paulo, could you talk for just a second, maybe pick the top 1, 2, 3, or 4 specifications and really what should a designer about to slot in a power module be thinking about and looking for on a data sheet like this?
Thank you, John. Let's continue our discussions about modules, okay? First of all, you have to consider that the most important thing is your application. You have to look to the spec always with a vision of what is your application. Second, forget about typicals. Typicals, you don't want your system to typically work. So you should use the minimum specs or the maximum specs, depend on the condition or the spec itself. So forget typical and go for the minimum in terms of power, intermodulation, things like that, and go for maximum, for example, for frequency response, maximum variation of frequency response. Okay? Second, it's very, very important to know that some of these parameters, although they are specified, they don't mean too much. For example, intermodulation, okay, and IP3. You have to be very careful with these two measurements because in a Class AB amplifier, intermodulation have a variation that's not going to be linear in respect to the output power. It's not going to be used 1 to 2 variation that we usually think about it when we are talking about a Class A amplifier or low noise amplifier. So please find where the specification is being done. And usually see the intermodulation with 6 dB per minus 6 dB per carrier from the nominal power. Second, IP3. IP3 varies in a Class AB amplifier because intermodulation varies in a non-linear format. Okay, so it doesn't mean too much the IP3 because you can't predict the performance of the amplifier in this case. And P1 dB. P1 dB is a very difficult measurement. I prefer to use CCDF curves because they don't consider the variation of temperature on the device gain. Okay, so we will talk about that later on in these slides.
And so, Paulo, then in building on your comments from the last slide and recognizing that application considerations are at the top of the list, how does something like that apply to whether you're going broadband or narrowband? Can you talk for just a minute about some of those trade-offs and important decision criteria?
First of all, it's very difficult to define what's narrowband and what's broadband. We have a customer that wants an amplifier that goes 1.7 gigahertz to 2.2 gigahertz. And for me, this is narrowband. For them, it's broadband. So it's very difficult to be very clear what that means. In general, narrowband will be an amplifier that is applied to a short band, a small band, and the broadband covers octaves or 1 octave or more. In our world of power amplifier design, it's important to know that the broadband amplifier usually have less efficiency and it has less power than a narrowband. So a device that's defined as a 500 watts device, you need to be careful to see if you can. It will give you 500 watts in the whole band or 500 watts in a narrow band. And when you broaden it, when you make it broadband, it will reduce the power. You might not be able anymore to get the 500 watts of this device, but you're going to get 300 watts. So narrowband and broadband has not just an impact on the bandwidth that you are transmitting, but also in the efficiency and the power that you can operate. Okay. There is one important thing. When you some of the device, another question is the device that you are used on the amplifier being pre-matched or not matched at all? Okay, if it's pre-matched or fully matched, it will be more narrowband by nature because the device will have the matching network inside the package. If it's pre-matched, it will have a limitation on the higher end of the band because what the device manufacturers do is that they increase slightly the impedance on the gate of the device or the gate of the device. Okay, so that's easier to match to the input, but that limits the higher frequency of the band. And so you have, this is something that the designers are considering when they do an amplifier. The amplifiers that has matched, for example, they are very good to be used, for example, in narrowband applications. Per se, S-band, C-band, X-band devices, they are matched to those bands. It's also, it happens also in the broadcast area where the devices are matched for the broadcast frequencies. And some of them are matched on the L-band side. So there are some devices that are matched to a certain part of the band, and they derive amplifiers that are narrowband. The other aspect of it is in respect to the efficiency is, for example, you can use Doherty amplifiers, which has the transformer at the end, the combined transformer that will be narrowband. They have very high efficiency, okay, because part of the device is operating class C. They are very usable for communication or telecommunication or broadcast.
So Paulo, thanks for that discussion. And it is clear that application-specific considerations are a huge part of this. And you mentioned on the other slide the importance of linearity in a communications application as an example. Linearity is one of those topics that I feel like gets maybe misunderstood, potentially miscommunicated in terms of either A, its importance, B, how you handle it, or C, where it matters and where it doesn't. This slide tees that conversation up, and I would ask you, can you please elaborate in terms of the trade space, the calculations, and ultimately the results if somebody has said linearity is a key criteria in my power amplifier application. Talk about that for us, please.
In most cases, in power amplifier is all about linearity. Okay, and linearity would be, mathematically speaking, is that the output of a device that is being stimulated by a function in the input will be directly proportional to that input, not generating any other sub frequencies or emissions. So it would be fully proportional to the input. That's very ideal. It doesn't happen, okay, because devices are physical components and they have nonlinearities intrinsically to the physical construction of devices or tubes or whatever you are using as an active device. So taking that in consideration, there are always components, okay? You can approximate it as a series of Taylor, or you can approximate it as a function, a Bessel function, depending on the amplifier you are building on. But in general, they have multiple other frequencies than the original frequency of stimulation, okay? And that's what shows their nonlinearity. There are very, very important things to consider, okay? Let's say that we decided that P1 dB is our measurement of linearity and intermodulation, together with intermodulation, IM3s, okay? So let's consider that P1 dB first. If you use a CW carrier, a sine wave carrier, okay, and you excited the amplifier with that sine wave signal, the problem is that, and you consider the point that the output doesn't go up 1 dB less than it would be if the amplifier is full linear, okay? What will happen is that you are not considering the loss of power caused by the temperature of the device. And in this case, the class A of the amplifier is essential. A class A and a class AB amplifier will have different behaviors or different performance. In a class A amplifier, because it's fully biased, the junction temperature is very high from the beginning. As you increase the input power and the output power goes up, what happens is that part of the temperature of the device is being transferred to the load, okay? And you will have a false impression that your P1 dB is higher than it is in reality, because now you are increasing the gain of the PA. In a class AB amplifier, the opposite occurs. What happens is that as you increase your input power, the current goes up, and the power dissipation in absolute value goes up in the device, and the junction temperature tends to increase, and therefore the gain goes down using the formula minus 0.012 dB per degree C of the junction, okay? So what happens in this case is that you're going to have an impression, a wrong impression, that the P1 dB is lower than it is in reality, when you are using a Class AB amplifier. So that distinction has to be very clear in your mind when you're choosing a PA. So in our case, in Empower, we use a lot the CCDF, the complementary cumulative distribution function, to define our P1 dB. And why is that? Because that's considering that the junction temperature is an unstable condition. And when we increase the power, we see the peak to average ratio going down 1 dB to define the P1 dB of the amplifier. It's much more consistent with the amplifier itself. Okay, so it's very important to distinguish these two things in terms of P1 dB as linearity. The other aspect of it is the third order intermodulation, which will define how much of the other components, the higher order components like F square, F cubic, are being part of your transfer function in your amplifier. And usually we consider that important is not only the IM3, it's the IM5, IM7, IM9. You have to know all this distribution to see how linear your amplifier is. And last, you have to see if the right side and the left side of the intermodulation on the spectrum, if they are equivalent in terms of power. If they are not, okay, if what you have in the left side of the two-tone carrier and what you have in the right side of the two-tone carriers are not in the same amplitude, means that you have some problems in terms of video filtering in the amplifier. And that's why you have the different IM3s left side and right side. Okay? Or they say down and up to the frequency that you are testing.
We've included a slide here to just highlight a survey overview of semiconductor devices that are likely to be used in power amplifier modules. Empower RF Systems uses a large percentage of our work is done with gallium nitride on silicon carbide and to a lesser extent LDMOS for some of the lower frequency work that we do. I'm not going to go through every element on this slide, but we've included it in the deck just for completeness and again to map out some of the things that you as a power amplifier module consumer might want to be aware of or asking about depending on the modules that you're looking at. The next slide goes into a lot more detail on gallium nitride on silicon carbide, and I'm going to leave that to Paulo.
With regards to GaN device, this is a very interesting table because that represents the device that we usually use in power. It is commercially available device and they go up to 6 gigahertz. For our applications and what Empower does in the solid state high power amplifiers. It's interesting to understand the great advantage that GaN has. GaN has a very high voltage breakdown, which allows it to operate at a very high VDS voltage. And also very, very important is that when it is subject to VSWR, the main reason that devices burn fast is the voltage breakdown. It's not the power dissipation. Power dissipation takes microseconds to burn a device. So the VSWR sensors can be good enough in general to protect devices. In terms of voltage breakdown, it's in hundreds of nanoseconds the device is blown. So you need to act much, much faster. That's one advantage that GaN has because it's having a very high voltage breakdown. It's much more difficult to burn it caused by VSWR voltage breakdown. It's also very high gain devices, okay, and it has very high efficiency. and that allows it to be used in a very large scope of applications. We, particularly in Empower, we like a lot to use the GaN devices with silicon carbide, and I will come back to that because it provides very high gain, very high efficiency, and very broadband. The intrinsic capacitance of the device is lower and allows for good matching, good broadband match. It's easy to match a GaN device in 1 octave of bandwidth. In reality, we almost say that 1 octave is narrow band, it's not broadband. So, and the other aspect of GaN that's important is the soft compression. In most cases, GaN device soft compresses slowly, and that makes the 3 dB, the compression of 3 dB much higher in power than usually you will have in LDMOS and GASFET, who roll over very fast. So GaN device in our case is very, very, very important because it allows us much more flexibility in design amplifiers that will be used by our customers.
So not every application that's out there can be met by a single module. And what you're going to be faced with at that point is combining discrete power modules. There's an illustration shown here which sort of highlights how we do things. But importantly for you, the designer, and you who will be using discrete power modules, we did want to point out a couple of tips and tricks or things to be mindful of when you're combining multiple modules into a higher power application. Paulo, how about sharing with us your knowledge, considerations for combining?
So I will not talk here about what we do. The illustration is just an illustration, as you can see, how we do our stuff. But the important point is split, the input splitter. Okay, you have to be sure that all ports of the splitter have the same amplitude and same phase, and they matched. Second, the cable that interconnects the output of the splitter to the input of your modules, the modules that you are going to combine, has to be perfectly matched cables. And they have to be high quality because cables, if they have different bands, they can change phase differently. Okay, so there are cables, special cables that keep the phase no matter what way you bend this cable or not. The same thing applies to the combiner. The combiner, the connection between your modules and your combiner needs to use perfectly phase-matched cables and cables that are stable for phase and amplitude. So those are special cables, and you need to be sure that you are using the correct cables. Usually it's very good to use combiners that have isolation, okay, so that the imbalance between them is dissipated in isolated loads. The other aspect of it is that you have to be sure that your impedance matching is correct between the input splitters and the amplifiers and your combiner. So the matching of all these impedance have to be better than 13, 14 dB return loss, at least. Okay, so, and the last but not least is that you have to be sure that the phase between the amplifiers is plus minus 15 degrees in any frequency of operation, and the gain matching is plus minus half a dB in any frequency of operation. So please it's not easy to combine it very efficiently. Sometimes you're going to put two 100 watts amplifier and you're going to get 110 at the output or 120 and not much more than that. Okay, so the concerns are in respect to the phase and to the gain. Plus minus 15 degrees phase match will cause a 0.3 dB loss in the combining. So you'll see that you cannot start to go much more than that. You're going to lose 1 dB or more just because the phase is not correct. All right? Now you add frequency. Higher frequency, the higher the frequency, the more complex it is. And last, you have to consider that you have losses everywhere. So between the splitter have some losses, the cable between the splitter and the amplifier has losses, the connectors have losses, and the same thing on the side of the combiner.
Thank you, Paulo. Wow, that's a lot of information to absorb, but fortunately now we're going to give everybody's brain a rest, and Jon and I will talk about a couple of module applications before we wrap it up. Touching on a real-world broadband versus narrowband topic is the wireless data link, and here are a couple examples with a broadband module made sense. Now, commercial narrowband wireless applications are typically not a fit for broadband module. However, specialty datacom, or for the DoD and public safety, what we refer to as tactical comms, are applications which have requirements beyond commercial cellular. For example, in the HF to UHF, there are companies providing datacomms, monitoring and control, encrypted but at lower data rates for railroad, mining, and power grid switchgear, for example, and they sell it globally. Broadband's the key because multiple frequencies are involved. A single transmitter design integrating a particular PA can be configured for use anywhere on the globe depending on the region's unlicensed bands. The linearity, what I'm showing here is the 1094. The linearity is good. It performs well enough with digital modulation. Its cost is good and is an inventoried module at RFPD. And speaking to value, it includes extra features that support integration, gain control, built-in fast switching, and current limit protection. And in some cases, the module's bias current can be adjusted either at the factory or by the integrator. You can consult us for questions on that. Now, the second application use case is a cellular network test range where our 1208 module is used. And yeah, that reminds me, another one comes to mind, not shown, is the disaster emergency mobile cellular towers, also using the 1208. And in both of those cases, they're operating at several commercial wireless frequencies, so a broadband COTS PA module has a definite integration and cost advantage over a system that would include multiple narrowband PAs to be integrated. And what might come as a surprise here is the linearity and the adjacent channel power ratio are good enough to mimic a cell tower on a low call density test range. And in the case of mobile cellular tower mimicking for emergency disaster relief, for example, this application, an additional cavity filter was used for increased performance. But again, a common theme, a broadband COTS PA module has a definite integration advantage over a system that would otherwise require multiple narrowband PAs.
Our last illustration today, before we move to Q&A, touches on counter UAS. It is certainly a very important application, and as highlighted on the slide here, and the importance of the power modules for selection, for consideration, you're matching up the frequencies that are in that domain of counter UAS and comparing those to the frequency and power levels that are available from our COTS modules and available from inventory at RFPD. These match up extremely well. These modules in varying degrees are designed into tactical platforms that are currently deployed in this important application.
That completes our slides and formal presentation, and thanks to everybody for your time and attention. As we hand this back over to the Global Spec moderator, I did just want to acknowledge Richardson RFPD for their sponsorship. And if we were in person, I would say let's give a round of applause to Paulo Correa, our CTO, and Jon Jacocks, our CEO. Well done, guys. And with that, I'd like to open it up to questions.
All right, gentlemen, thank you so much for that great presentation. So we are going to move into some of our live questions right now from the attendees. So, gentlemen, we're going to move into our first question. This person is asking, you have talked about gain and phase matching when combining modules for higher output power. What other module or system-level interface elements will impact combining results as well?
And Paulo, I think if you can elaborate a little bit on that. I know in your slide we talked about cables, we talked about cable bins, a little bit about connectors. Short of anything proprietary that we might be doing, Paulo, can you add a little more color around, I guess, tips and tricks or other things to be cognizant of when combining multiple modules?
Yes, thank you, John, and good morning, everybody, or good afternoon. I don't know where you are. But for me, what we do in Empower is that we add what we call a vector modulator to combine modules or to combine chassis or boosters. We use a vector modulator where we control the phase and the amplitude in a broadband way. That is, a narrow band vector modulator will not solve the problem if you have a broadband amplifier. The other thing that we do is we measure the power dissipated on the isolated load so that we can optimize the power to the output of the amplifier, not on the isolated load. So those are tricks that we use, and it's very important. Besides, you have to understand that all the cables have to be really matched, because if they vary, you're going to have losses when you combine amplifiers.
Thanks for that, Paulo. Katie, what's our
All right,
next
great,
question?
Paulo. Thank you so much. So for our attendees, as I mentioned, if you have a question today, go ahead and place it into that window and click Submit. I also wanted to point out a couple of resources that we have listed in our resource widget. If you look down below the main window, you will see the resource window. There's some items listed there today. If you'd like to click on those and take them with you, now would be the time to do that as well. All right, gentlemen, next question here from an attendee. Is there any advice on using a module in an application where there is little airflow? How do I cool it?
Yes, in this case, it's also very simple, okay? You can use a good heat sink, a very good, and this is very important, is the interface between the amplifier and the heat sink. And you have to use the appropriate interface. And also you can add a fan if you don't have enough flow. So usually this is what's used, and that's very common in power amplifier applications.
Okay, great, Paulo. Thank you so much for that answer. All right, another one here. Are there cases where you can trade bandwidth for more peak power?
Yes, that's true, okay? For example, if you're operating in the infrastructure cell phone frequencies, you're not going to use broadband because your efficiency is going to be so low, and you multiply that by the number of cells, and your cost of energy is going to be very high. So it's very, very good to use narrowband amplifiers in this case to improve the power consumption. In other case, for example, is S-band or C-band radar. The bandwidth that you are using is narrow, relatively narrow, and you should optimize for those frequencies. Same way with the X-band, and another way, another application that's important is in Ku-band, satellite uplink. So there are multiple applications that narrowband is very, very important and better than broadband.
Okay, great. Thank you so much for that answer. We've got a couple more questions from our attendees here. This next person is asking, what kind of self-protection is inside the typical module? Do I have to add any protection?
Oh, that's a very good question. There are things that you need to add. Usually in a module, what we have is protections of overcurrent and protection for temperature, but usually we don't have protection for VSWR. And in this case, it's important to add a directional coupler and a system that protects the amplifier against VSWR.
Okay, great. Thank you so much. For all of our attendees, as a reminder, if you have a question now, please enter it into the Q&A window, and we will answer a lot of the questions following today's webinar. But if you have a question today, now would be the time to enter it. All right, gentlemen, we have a couple more here. Next one is asking, when protecting against high reverse power, how fast does the protection loop have to act?
Yes. Yes, again, here is what I said during the webinar. If your VSWR can cause voltage breakdown, you need to act in about 200 nanoseconds. If your device is protected against voltage breakdown, then you have power dissipation. And power dissipation will take a few microseconds to damage the device. So when it's voltage breakdown, you need to act faster. When it is power dissipation, it's microseconds. Okay, it doesn't mean too much when you say that your amplifier will withstand a VSWR of so much for 1 minute or 5 minutes. It means nothing, because in reality the junction temperature goes high much, much faster. And if it's voltage breakdown, it doesn't matter. It goes in nanoseconds. You damage your amplifier.
All right, thank you so much for that answer. Our next question here, what is the operating temperature for those GaN-based PAs?
Okay, the maximum temperature, junction temperature is about 225 degrees C. We don't like to operate the device, the junction temperature, higher than 180. And that's where we do. But to calculate the junction temperature is not very easy, because you need to know exactly what is the power dissipated in the device, which is different even from the voltage multiplied by current in the oscillar side and the power that goes to the load, because you have lost in the matching circuits inside the amplifier. So it's not very easy to know that. Usually what we do is that we don't allow the base plates to be higher than 85 degrees C. So we usually protect it at 85 degrees C at the point that we can measure the temperature. And that's what we do. Our sensor, our thermal sensor, is very close to the case of the device, and we can measure with very good accuracy what's the temperature of the flange.
Okay, great. Thank you so much for that answer. We do have time for a couple more here. So the next one is, if my application only requires a high-power CW signal output, is it okay to use a Class AB amplifier with external filters to filter off its harmonics and spurs and operate it near its PSAT for maximum power?
Yes, that's a very good question, and it is correct. You can get it as maximum power as possible when you only need CW. You generated, you can go very close to saturation, which for us in power means 3 dB compression. We usually have to be very careful only on the temperature, because as you know, in a Class AB amplifier, as you increase the power, although you have more efficiency, you also increase the power dissipated during the device. That's all you need to care about is the temperature.
Okay, great. Thank you so much for that answer. So we do have about 10 minutes left in the webinar, so we are going to take one more question and then start to wrap things up. So this last question matches up well with the one we just did, Paulo. This person is asking, when would you use a Class A amplifier instead of a Class AB?
In this case, it's very simple also, okay? You use Class A amplifier when you don't care about the efficiency of the amplifier, you have plenty of power, you can dissipate the temperature, okay? You can dissipate the power, the heat load of the amplifier, and you care only about linearity. That's when you use Class A. Another way is when you have an LNA. An LNA is perfect to be used as a Class A amplifier. So basically, it's linearity. If you want linearity and you don't care about efficiency, you can use a Class A amplifier.
Okay, perfect. And then just to kind of round out that last answer, we are going to take this last one here. I think it fits well with the other two. So, Paulo, what are the long-term effects of operating a Class AB amplifier near PSAT or at PSAT?
Oh, the problem is that usually what happens is that the amplifier can have a degradation of power over time. So, again, the most important thing in this case is to be sure that you operate with lower temperature at the junction. The most important part is that will make your amplifier last longer. If you look at the MTTF curves of the device, you're going to see that as you increase the junction temperature, the lifetime of the amplifier of the device goes down. So again, the important thing on a power amplifier is to care about the temperature that is operating the device. That will make the device last longer and have less loss of performance over time. The other thing that's important, but that's usually the design problem, is to care about the gate currents so that you don't cause the device to be overdriven and burned because of overdrive condition. And talk about overdrive condition, that is another issue that should be protected on an amplifier that's not protected on the module itself. It needs to be added to protect the system, the module.
Okay, great, Paulo. Thank you so much for that last answer. As I mentioned, we are getting close to the top of the hour, so we are going to start to wrap things up right now. first I would like to say a huge thank you to all of the presenters today, Jon, George, and Paulo. Thank you all so much for the great presentation and for answering some of our attendees' questions. We enjoyed having all of you.
Thanks, Katie.
Thank you.
Thanks a lot. And again, this is Jon Jacocks. Just thanks to Global Spec and RFPD, Richardson RFPD, our partner. Excited and really pleased to be able to connect with everybody today. Thanks again.
All right, thank you, gentlemen. Again, thank you all for taking time to attend this webinar event. Take care, and we will speak with all of you soon.